So it's my pleasure to give such a lecture. The topic of my topic is a basic principle of interferometry and its application in national monitoring. I'm Chou Xie from ICAS. In my slide, I would like to give I have four parts. First, I would like to give a short introduction of the consequence of interferometry. Then, I would like to analyze the composition of interference phase. After that, I would like to analyze the factors affecting interferometry. After that, I would like to show you some application of interferometry. At last, I will give a short introduction about interferometric related software. First, I would like to give a short definition of SAR and interferometry. SAR is a kind of microwave front-end device. It uses the movement of a flying platform carrying a radar to orbit non-sensitive antenna, thereby obtaining a high-resolution images. For SAR interferometry, it uses two SAR antennas to obtain two coherent single-look complex image in the same arrow to obtain surface elevation information or surface deformation information from the interferometric phase information. Just as shown in this thing. For interferometric system, there are two different systems. One is called monostatic systems. In monostatic systems, the same antennas act as both of the transmitter and the receiver. Switch from one mode to another thousands of times a second. In other words, a radar inverts. The transmitter and the receiver share one antenna. Most of the satellite system is monostatic system, such as Cosmo, Alos 1, Alos 2, Amistad ASA. At the same time, there is a larger interferometric system called bistatic INSA system. For in INSA bistatic system, two antennas act as the transmitter and the receiver meter respectively. This kind of INSA system is used on SRTM 2000, and at the same time, Terrastar system also supply bistatic system to get the global elevation. Now I would like to show you the physical meaning of the surface. The singular received by the spacebound radar S1 and S2 can be expressed as the following formulas. S1 and S2 usually receive the phase constants two parts. One is for the phase determined by single round trip phase. And the other part is the random phase generated by the inference of surface scatter and transmission patterns factor during the propagation process. If you want to calculate the star interferograms, we should give some assumption. First, we would like to ignore the inference of noise, and then we should assume that surface scatter remains unchanged. Based on this assumption, the star interferograms can be expressed as this formula. For monostatic system, delta T, transmit time equals to 2 delta R equal to divided 2 delta R divided 2 delta by C. C means the speed of light. For this static system, delta T equals to delta R divided by C. Although the phase difference of a single image is random, the phase of the interference is meaningful, and it is determined by a single phase difference. These figures show that A is the amplitude, phi1 and phi2 are the phase. If we look at the phi1 and phi2, we cannot see anything. It didn't have this kind of phase is random. But if we subtract phi1 by phi2, then we can find there are some information from the phase image. Then I would like to analyze the composition of the interferometric phase. While the phase value of a single star sky are of low practical use, and the difference of phase value between the two star acquisition can allow us to estimate range variation with a very high accuracy. InSAR technology InSAR technology makes full use of the phase information carried by the echo symbol to obtain the three-dimensional information of ground or the information of surface deformation. The base data sample to calculate the distance through the phase difference between two echo singles corresponding to the same target. Due to the influence of the surface geometric relationship of the infra system, the phase difference of the point with the same height in the azimuth direction or the distance upwards should remain unchanged on the interferograms, or cause the phase of the interferograms to shift. Even flat ground without height information would also produce linearly changed interference phase. As shown in the figure, P1, P, and eavesdropper P are the same, but the slight distance is what the sunlight obtained. P and P and eavesdropper P as well as 2 are different, and the value angle also have a slight change. Therefore, in order to obtain the phase that accurately reflects the height information of the target, I have to perform the 11 methods. Then we could set up the relationship between the phase and the flat phase and the baseline parameter. Due to the different horizontal vegetation from the target P and eavesdropper P with the same height produce linear change phase in interferograms. This formula is called flat phase. It can be seen from the formula that linear change interferometric phase would also be produced by on a flat ground without elevation change. The change of difference, as shown in this figure, the change of also called the regular flange change. Moreover, the regular finger is very dense, often covering the top graph fingers, cause the interferometric finger to look like a dense flat fringe. And then we should remove the flat edge finger first. When we subtract the flat edge phase from the initial from the interferometric phase, we can find the recital phase is related to the elevation. Since the radius of the flat strip, finger changes quickly, if it cannot be effectively removed, the phase unwrapping would not only lead to interfacing, but more seriously, it may cause unwrapping error, and such error can be propagate, which will affect the accuracy of the generated DM. Then I would like to talk something about elevation phase. Due to different elevation, the phase would also change. And the interferometric phase of ground target P and P atmospheric phase can be represented by two different formula. And the interferometric phase difference between the ground targets P and P atmospheric phase can be represented as this one. Based on the assumption data sheet is usually very small, we can set up a relationship between the phase and elevation. We also can get a formula to represent elevation ambiguity. Based on the formula, we can find this interferometric phase represents the topographic phase of at the color. The height of the color is about 1,040 meters. When the proper baseline equals to 70 meters, we can the height of at the color can be showed use seven cycle of friends. So one cycle friend represents 200 meters. When the capital baseline equal to 250 meters, the elevation, the digital elevation friend is very dense, and one cycle of friend represents 40 meters height difference. So the normal or the perpendicular baseline is a king parameter in some interferometry. The elevation of the surface gives to the flatted interferograms. The different phases can be present as the fellow formula, and the attitude of the elevation ambiguity is equal to about 10,000. So when the perpendicular baseline equals to 120 and the elevation ambiguity equals to 80 meters. These two fingers give a clearly relationship about clearly showed clearly elevation and ambiguity. Then I would like to talk something about deformation phase. If a scatter on the ground slightly changes its relative position in the time interval between the two star acquisitions, such as sudden landslide earthquakes. Then and additive phase time independent of the baseline period. This is called deformation phase. The formula of the deformation phase is very simple. D is the relative scatter displacement projected on the slant rand direction. This one show deformation for movement on a glacier. If the propagation medium changes in the time interval between the two star acquisition, such as humidity, temperature, pressure. So, the phase about then the atmosphere screen phase will appear. Atmosphere is homogeneous due to the variation in pressure, temperature, humidity, affluence, light speed, the velocity. The delay variation in the repeated interval results in a phase screen, hence a noise. Atmospheric noise is a fractal power spectrum. Hence, it is correlated in space. Coherence maps cannot measure this noise. At most, artifact can't be up to 2 fingers. It is converted in elevation arrow. Depends on the baseline. The arrow cannot be estimated or recovered. So, if we want to correlation the atmospheric screen phase, the change of refractivity or dVW can be inferred from the Jaweria model. Global or regional. We also could use multi-spectral remote sensing, such as modes and marries to infer change of the atmospheric screen phase. At the same time, GPS and radar signal could also be used to inform the atmospheric phase. As a result, can be used to combine all the available information to atmospheric phase. To sum up, the composition of the interferometric phase is about a flat earth phase, elevation phase, displacement phase, atmosphere phase, and noise phase. Here give the formula of flat earth phase, elevation phase, and displacement phase. After we analyze the composition of interferometric phase, I would like to show you how to generate interferograms. To generate interferograms, we should get two SLC data, and based on the orbit information, we can register and resample the two SLC data. With local frequency estimate, we can do spectral shift and common band filtering. After that, with coherence estimate, we can get a coherence map. After flattering, we can remove the flat edge phase. Then we got interferograms. In this slide, I would like to talk noisy source in interferograms. For evaluate noisy performance, the interferogram phase difference is assumed to be 0. It includes sense correlations noise, such as temporal noise, volume noise, geometric noise, and the system decorrelation noise, such as thermal, quantization, and analyze noise. The complex interferograms phase to pixel contain singular and noise contribution. We are interested in the phase noise as the phase is singular. Phase static is known for homogeneous target. Phase STD can be expressed in the image SNR. The cover holds for one look. For pure noise, SNR is hardly invertible. That would be useful to estimate multi-look averaged performance. Coherence can also be estimated in each pixel by averaging over area of stationary phase. Topographic phase phi is assumed locally flat, hence it can be retrieved by means of instantaneous frequency estimation. Coherence is based when freedom degree is 1 or when 1 scatter prevails. Here show the amplitude of image on Amazon arrow. The second one is interferometric phase. The last one is coherence phase. The coherence on the mountain arrow is very low, and also the coherence is also very low on the river. Coherence maps are very useful for two purposes. They can provide a local measure of quantity, such as dam accuracy, and also provide useful and quantitative information on sense features. These information are complementary with intensity image. Here, I would like to use ITA as an example to show the presence coherence maps got on different time. We can find at a different time, different arrow have a different coherence. If we mosaic it together, we can use it to classify different ground target. Here show the difficult sense in interferograms is called two-dimensional phase unwrapping. For unwrapping, we should find vertices or residuals. Residuals cannot be found by inspection since data are low on the sample degree. However, it is enough to compute the shortlist line integral on a score of 4 samples around the vertex. Based on kinds of assumption, residuals can be found due to the topography or the noise. Here show a very simple example of how to get unwrapping. Here is low. The first one is orange phase, and here show the rotational phase, and This one is unwrapped irregular phase. And here is the rotational phase. So for unwrapping phase, clearly we should find a good solution from the wrapped phase. There are three kinds of different type of solution for unwrapping. One is called L0 normal minimize the global cut length. The second one is L1 normal minimize the total number of the multiple of 2 pi to be added on each face. The last one is L2 normal minimize the energy of the arrow between the computer slopes and the one to be reconstructed. Now I would like to discuss the impact of phase noise system zero loss. I think there are four kinds of influence interferometric accuracy. First is the phase noise. It includes the system thermal noise, spatial baseline decoherence, droplet decoherence, temporal decoherence, data precision decoherence, and artifacts that would cause phase error in the interferogram generation. And the second one is the influence of satellite orbit error. And also data and elevation data error would also influence the accuracy of displacement level. And as we have mentioned in the front slide, atmosphere disturbance also influence the accuracy of the interferometry. This image shows the time coherence. The above three fingers are three-band interferometry from EIS, from Elicit A side, and below three fingers are from L band. LS2, we could get the solution that long wavelengths can infer inside data can sustain high coherence over a very long temporal interval. Here is also these two fingers show the coherence loss as a function of time. Although polygenic fashion remains coherence over very long time intervals, such as events. But the meditation cannot remain high coherence. Coherence represents the phase variation estimation. Coherence can be assigned to each pixels. It needs many simultaneous acquired star image to evaluate expectation. Here show 3.5 year interferograms. Left one is estimate coherence by one times one look, and B represents coherence by 5 times 20, and we can find in the other arrow we can get phase in the vegetation arrow we cannot find any information. Reduce the coherence or decorrelation is associated with the increase in the variation of the interferometric phase. Totally, the correlation is related to the baseline of geometric decorrelation and the Doppler central decorrelation and the patchy of the radar wave to the scatter medium and the semi-correlation. Here give indicators of geometric decorrelation. They show how to calculate the Doppler central decorrelation and how to calculate the temporal decorrelation. This figure clearly shows with the increase of the with the frequency and the coherence lost greatly. The loss of correlation is due to the movement of vegetation or the electric change or the volume of vegetation. Because the eastbound got the return singular from the canopy of the forest, and the P-band can get the information from the ground. It can penetrate the surface of the forest. Here gave a simulated coherence model. Based on the coherence model, all the interferometrics can be analyzed together. It's called the time series analysis. This kind of time series insight can be developed to persistent scatter method or small baseline method. PSI first be presented by Faraday, sparse first presented by Dilo in 2002. DS package can widely extended exist on the natural surface. Combined PS and DS can obtain more spatial samples, thereby obtain more reliable spatial temporal wrapping. More information can be got by combined PS and DS method. Here give a phase difference between two PS. Because this formula is very complicated, so I would like to go to another slide. There is a thing to how to compute the 3D phase unwrapping. then we can get displace time zeros or displace velocity. Here show the flow chart of permanent scatter technology. Now I would like to show you something about application of interferometry. INSAR can be used to analyze earthquake cosmic deformation and also used to landslide detection. In urban arrow, it can be used to detect subsidence. And in China, it also used to monitor frozen soil road banks. And oil and gas marine subsidence can also be monitored. I also do some thing about wetland hydrological environment monitoring. I would like to use Wenchuan earthquake as an example. INSAR can be used to analyze cosmic deformation monitoring. From these interferograms, we can find that the interferometric pamod is deformed into up and low parts with the fault zone as the boundary. On both sides of the fault zone, there are two obvious differences in digital ground formation. The interferometric friends on the bottom of the wall of the fault zone are related smoothly and the deformation amplitude is slow. However, the interferometric friends on the hound wall of the fault zone are dense and very fuzzy, and the deformation amplitude is large. Use the side image pi before the accuracy of the landslide to perform interferometry. The deformation error of the INSAR is very consistent with the position of the landslide, which proved a new technology mean for detecting potential landslide in advance. But we showed motion that INSAR can only efficiently monitor slowly deformed landslide. With the assistance of GIS technology, it provides a large number of data sources for GIS through the direct investigation and monitoring, and rely on the powerful spatial analysis capability of the GIS to predict the landslide desert. Here show you the Chinese GF3 data, some data to do landslide recognition. We obtained the GF3 full polarization data on 2016. The closed landslide developed the south foot of the mountain with gravel at the mountain component covered by the vegetation. The surface scar is very strong and can be clearly identified. Here show the result got from time zeros analyzed by dataset 2. We can easily find the closed arrow of the landslide. For subsilence in other arrow. Non-standard subsilence is generally slow with a time span of several years. So, time coherence and atmospheric influence have become the main factor restricting the application of insight to non-subsilence. Here show result for Zhejiang arrow. We can find several subsilence in Shaoshan arrow, and here is because in this arrow because the people, because the factories in this arrow, we found a lot of underground water to development economy. Here is the time series information, and these can also be used to detect marine subsidence. We can clearly find the arrows surrounded by the purple circles in the frame represent the subsidence arrow formed by core meaning. Here show how to use insight to get to detect the deformation on prison to Tibet, Shanghai-Tibet highway, and it can also be used to detect oil and gas marine subsidence. Here is some example of how to use it to detect water level change in wetland. Based on some assumption, we can get the absolute water level zeros.
谢老师。内容还多吗？时间好像。
结束了。好的。In the last slide, I would like to show you some free software and commercial software to detect to do something about the interferograms. So thanks for your attention.
Thank you, Dr. Xie. Very good presentation. Thank you very much.
Thank you.
And there.
Thank you, Professor. Very wonderful.
There are questions from Chinese. You can open your chat box, Dr. Xie. Please open your chat box. 聊天的那个窗口。
Chat box. Okay. So I should stop. 屏幕共享 screen share. Wait a moment. 停止视频，暂停共享，停止共享。Yeah.
Have you seen question 1?
No, I don't see question 1.
在聊天点那个聊天。